Welcome to Chennai Mathematical Institute. This is the final session of the S.T.E.M.S lecture series at CMI as a part of Tessellate 2019. For the first lecture today, we have Professor Priyavrat Deshpande with us. He is a faculty of mathematics at CMI, mostly works in algebraic topology and combinatorics. Today he'll be talking to us about plausible reasoning, the science of guessing. So now I invite Professor Deshpande to start his lecture.
Aditya, is there a pen? Okay. Thanks. Welcome to everybody. I would like to thank the young and enthusiastic organizers for this lecture series and the invitation to talk here. So I think this will be the second time the S.T.E.M.S activity will take place, and the first S.T.E.M.S activity, which happened in January 2018, was already a success because of the number of participants and also the S.T.E.M.S workshop that happened in February. Anyway, so I would like to talk about guessing. Okay, or to say it concretely, I would like to talk about a slightly different way of doing mathematics, which most of us often don't encounter in our school days, because it's slightly difficult to teach in class. But I thought I would give you a glimpse of it, and we would like to do it using some interactive exercises. So I'm not really going to talk or tell you what this thing is and what are its various aspects, but I'm trying to, what I'll do is I'll come up with two problems. I have come up with two problems, and we will solve these problems together, and we'll sort of in that process, I'll tell you about what plausible reasoning or inductive reasoning is, and how it's a different way of understanding or doing mathematics. Okay, so let me start. So there's going to be a lot of interactions, because I'm going to ask you questions, not necessarily mathematical, but what you feel and what you think and what your ideas are. So just be ready to participate. So let me start with a question. So what is your perception about doing mathematics, or what has been your experience? Would any of you like to elaborate on that? How do you feel mathematics is learned, or what's your personal experience about learning mathematics, or what do you think are the peculiar characteristics of mathematics? Anybody? A few inputs. So I was just asking everybody, what is your feeling about mathematics, or to say it precise, what do you think, according to you, how do we learn mathematics, or how should one learn mathematics? Okay. Well, okay, so sorry. So let me precise. What do you think, how do you think one learns mathematics, or what's the best way to learn mathematics? Go ahead.
You should learn it yourself, and then you should see everyday problems and
Okay.
whatever you face in, like, for example, if I want to buy something that type, then if you have any doubt, you should ask the person.
Okay.
That way, like, learning it yourself is the best, because you understand it the way you want.
Okay. Sure. You want to add something?
Visualize patterns.
Okay. What do you mean by visualize patterns?
You see a trend in a certain way.
Okay.
Something changes.
Fine. Do you have anything sort of specific to add to this because it sounds very vague? I sort of get the feeling, but just to elaborate on this.
Like if you take a pad of a specific, like an event,
Okay.
and you take note down information about the event,
Okay.
and then you see the numbers change by
Okay.
a certain way.
Okay.
So by observing all that.
Okay.
Yeah.
So let me rephrase the question. So how would you compare learning physics with or learning biology against learning mathematics? How would you differentiate? Let's talk about science subjects. So what do you, according to you, how is learning physics different from learning mathematics? So do you learn physics by doing some experiments? Do you do that? How about biology? How about chemistry? You have experiments? A lot of them? So you have experiments in mathematics? Sorry? So have you done, so was experiments in mathematics a part of your learning process in school? No, okay. You think proving something is an experiment? Okay. Okay, but have you learned like this that, okay, here is a statement, we want to prove it, okay, let's try. And we tried different types of proofs, we tried different ideas in class, and now, okay, this is how an experiment in mathematics is done. Okay. Anything else anybody wants to add? Yes.
So what I noticed was in biology or chemistry, you have to remember lots of things.
Okay.
In math, it's like you only remember a part of it and you derive most of it from what you remember.
Okay. Okay.
So that was why I liked mathematics more than other subjects, that you don't have to remember stuff like in history or biology.
Okay. Okay. Fair enough. Yes, she wants to.
So I would think that there are lots of abstraction in mathematics, symbols and science and all that. I mean, how do we understand one?
Okay.
In that sense, it is very different from your real life experience.
Right. Yes.
So that way it is little, abstract.
Okay. Okay. Is there anything else? Yes, he wants to say something.
I felt biology and physics are empirical sciences where you conduct experiments and whatever theory you formulate has to be tied to the real world. But maths doesn't have to be like, we can create models and abstractions and it need not be attached to the real world.
Okay. So mathematics you do need not be associated directly with real life situations. But there are parts of physics where you do that, right? Where you sort of think of something which might not readily exist, or maybe we figure it out a bit later. Isn't that true?
Like I haven't taken a high level physics course, only school grades.
Sure. Okay. Yeah, I understand. Anything else anybody wants to add to this? Okay, so let me describe sort of a generic pattern. So the way most of us learn mathematics in school is we are introduced to a concept, right? And then we are given a bunch of rules. And then when we are supposed to solve a problem, we have to figure out the various concepts that play a role in that problem, and then we have to figure out which hypothesis is satisfied, maybe more than one statement, and then we are supposed to write it down logically, correct? So we have to arrive at a logical conclusion based on the rules that we have learned, and we have to figure out exactly which concept applies at a particular step when we are trying to derive logical conclusion, right? So either you prove something or you actually get an answer to, say, solving an equation, right? Or proving a statement. So let's say that these two things are different. Okay, so are you encouraged to guess in mathematics? What's your experience in school days? Were you encouraged to guess? So your teacher wrote a problem and said, okay, before you try solving it, why don't you guess an answer? Yeah. Sometimes, okay. But is it, according to you, is this something like this be allowed in mathematics or not? Okay. 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 So, is there anybody who would like to share their guessing experience in mathematics? Have you guessed enough, or were you encouraged to guess, or you're not allowed to guess in mathematics? You have to be very precise. If you give an answer, it has to be correct, or there's something wrong if you don't come up with the right answer. Is that what your feeling is? Okay, so okay, but that's more like when you want to write down a real number, your answer is a real number, and maybe you don't have sophisticated methods to write down the decimal expansion, so you estimate. But that's fine. So I'm not really talking about that. I'm talking about anything. You have to prove something, and whether you want to know this statement is true or false. So would you guess? Okay, this is true, or no, this is false, or something like this should work, something like this should not work, or you are sort of forced. First step is to figure out which statement or which concept you learned applies here. That should be the first step. Then you go looking for a hypothesis which is which fits a particular statement that is part of the rules that you have, and then you make sure that this thing fits, so you can apply this rule. Applying this rule gives you this sort of logical conclusion which you write down and then solve a problem. Is that generally what we do in mathematics? So what I want to do today is to demonstrate a different side of mathematics. This is a side of so the mathematics when it evolves, right? Somebody finds, or in past or even in the present day, when people try to find out new concepts or prove an entirely new theorem, this is not something that they would do. Okay, so they would, the general procedure would be very similar to a physics or a biology or a chemistry experiment, where you try to observe a phenomena. Okay, based on observations, you try to guess a pattern, and then you try to figure out why this is happening, how this is happening. Would something else happen instead? And then try to come up with the right question, okay, and formulate it as a theorem and write down a rigorous proof of it, which is, sort of a logical step followed by another logical step. Okay, so this is what I would like to do today, and this is slightly so. Now we would sort of discover whatever I just said using two problems in mathematics. Okay, so let me sort of simplify the analogy. So if you were doing research in chemistry, you would play around with chemicals. I'm just simplifying it. Okay, or if you're a biologist, let's say somebody who studies animals, they would go in forest and observe life cycle of a particular animal, right? So similarly in mathematics, we have, let's say, numbers, and we have some concepts from geometry. And then we would like to observe, and we would like to play around with them. We would like to do experiments with them, and then prove something or solve a problem or find a new theorem. Okay, so let's start with numbers. Okay, let's start with numbers. So I'm going to write down a formula, and we will. So again, this is sort of a. It cannot be too open-ended. So I'll to begin with, I'll pose a problem, a concrete problem, but we will sort of solve it using experiments, and we will try to guess what should be the answer to the problem. Okay, so let m be a positive integer. Okay, so we'll just deal with positive integers. Okay, so now I'm going to define a function from integers to integers, positive integers to positive integers. F of m. So given a positive integer, this function produces another positive integers according to the following rule. Okay, so if you haven't seen the symbol, let me just explain to you what this is. So this is the integer part. Okay, so this is the largest integer, smaller than square root of m. So let's say, what is this? So this is a perfect square, correct? Its square root is 2. 2 is an integer. Fine. Now 5 is not a perfect square, correct? But its square root is greater than 2. And 2 is the largest integer, smaller than the square root of 5. So this is also 2. Okay. Similarly, if you replace 5 by 6, the answer will still be 2. Okay. So this is the integer part. Is this clear what this function is? Okay. So this is my function. Okay. Okay. So as a first step, what I want you guys to do is, for various values of m, I want you to write down what f of m is. Okay. So I'm going to make a table here, m, f of m. Okay. So I'll give you, say, a minute, or even minute is a long time. So half a minute to write down. So let's say, what if m is 1, what should be f of m? Just loudly say. It's easy. 2, right? 1, and this is 1. So 1 plus 1? 2. Okay. If m is 2, what is f of m? 3. Because square root of 2, yeah, it's greater than 1. So the integer part is 1. Whatever it is, I don't care. But the integer part is 1. So 2 plus 1 is 3, right? 3. This is equal to 2 plus 1. Okay. 3. What's the integer part of square root of 3? 1. So 3 plus 1 is 4. Okay. What about 4? 6, correct. What about 5? 7, correct. What about 10? Okay, let's say whatever it is. What about 9? 12. What about 10? What's the integer part of the square root of 10? 3, 13. Okay. You guys want to try a few more and write them down in if you have writing material? Okay. So these are a few. I want you to write down a few more so that I would like to encourage you to find a pattern here. So based on this, can I just sort of, you want to, is there anybody who would like to guess something about this? Sorry? Go ahead. Just by looking at whatever I've written here, it's not much, right? There are infinitely many numbers. I've written a very few of them here. But is there anybody who would like to make a guess about how these function values change? Just guess. I mean, what's there? A really wild guess would be that after a while these values just stagnate, you know. They don't change. That's a really stupid guess, but yeah, go ahead.
Yeah, so first it increases by 1,
Okay.
but it moves in
Sorry?
odd numbers. So there's 3, there's 2, 3, 4.
Right.
Then after that there'll be 5 that will go in. Okay, the gap
Okay.
is 2, so I didn't think about the gap, but
Okay.
after it keeps moving, it's 2, 3, 4. Then
Okay.
after that it goes 6, 7, 8, 9, 10.
Okay.
So 3, then 5, then 7.
Okay.
That's how I
So you're saying that sort of it increases by 1 in clusters,
Yeah.
something like this?
Yeah, in class.
There are increments of 1 in a group, then suddenly there is a jump up or down, I don't know. Is it going up?
Yeah.
Okay, fine. So it's going up, but again there is an increment by 1. That's your guess. Okay, fine. Did any of you make similar observations? You can try, say, 50. Okay, let's try 50. So let me write it here. What is f of 50? 57. Why? Because, right. What about 51? 58. Okay. Oh, so there are increments. So maybe I should have started before 50. So let me write, let's say, what is f of 47? Why? 47 plus 6, correct. So 53. Okay. What about 48? 54. Okay. Excellent. What about 49? Is it 55? Is it 55 or not? 56. Okay. And then there is 57, 58. So there's a gap here, right? There was a gap here. And you said there was a gap after 8. So 8 was 10. And 9 is 12. So there's a gap here. Oh, so according to him, 15 goes to 18 and 16 goes to? Oh, there's a gap here. Okay, so 24 goes to 28. Okay, there's a gap. Okay, so why is there a gap? So something happens just before a perfect square appears, right? Is that what is happening? So, okay, so what is happening? Why is there a why is there a jump of 2? Sorry? Because this changes, correct. Easy, there's a very easy explanation to this, correct? We can actually prove this. Okay, see. Suppose you have a perfect square, correct? Let's say that perfect square is of the form k square, where k is some number. So what's going to happen? F of k square, according to our formula, is k square plus this thing, right? It's a perfect square. So the integer part is just the integer k. So it's k square plus k. Correct? Now, what is f of k square minus 1? This is k square minus, sorry. So this is k square minus 1 plus what? Plus what? K square minus 1 plus what? What is the integer part of square root of k square minus 1? That's my. What is this? Are you sure? This is k. So you're saying that the square root of k square minus 1 is equal to the square root of k square? Sorry. So, sorry? Huh? Mm-hmm. Are you sure? No, so what we want is a perfect square which is less than k square minus 1. Perfect square. So look at all perfect square which are less than k square minus 1. Among them, choose the largest. That's the definition here.
So if we take k as 4,
Mm-hmm.
then 16 minus 1, 15, root of 15, and the greatest perfect square less than
15 is?
it will be 4. No, it will be minus k minus 1. Sorry, k minus 1.
Okay. So this is
K square plus.
k square minus 1 plus k minus 1. Okay. Because the perfect square which is largest among all those perfect squares which are less than, yes, k square minus 1 is k minus 1. The square root of that is k minus 1. Is it clear? Now there is a change, right? So now you can see this is k square plus k minus 2. Correct? So there is a jump of 2. Correct? So we sort of saw a pattern. Based on that, we made an educated guess, not a wild guess. Correct? That there is a jump of 2 just before a perfect square appears here. Okay? Okay. So now what about the other numbers? What happens at f of k square plus 1? So this will be k square plus 1 plus k. Right? So it increases by 1. Right? What will happen at k square plus 2? Sorry. K square plus 2 is just k square plus 2 plus k. Right? So this plus k is not going to change unless you hit the next perfect square. And then there will be a jump of 2. And again, the time you hit the next perfect square will always increase by 1. In between it will always increase by 1. And when you hit the next perfect square, it will increase by 2. Right? So these were observations, and this is actually a proof, right? Because k is not a particular, any particular number. We have demonstrated that for a general n, this is a reason. Correct? Okay, so this could be made very precise, but I don't want to spend time, writing a very rigorous proof. But this is the crux of the idea, is that this is a behavior. Okay, but that's just a part of the story. What I would really like to do is I would like to see what happens if you successively apply this function. Okay, you keep applying this. So we have found f of m, right? Now my f of m is input to f, and I would like to see what is f of m, and then I would like to see what is f of m, and so on. Okay, so let's try that. So let me erase this and try to make a longer table. Okay, so I want to make things more interesting, possibly. Okay. Okay. So I'm going to just invent a notation here. F of m as short, I'll write f raised to 2 of m. This basically means that you apply f to f of m again. Okay. So we found out that f of 1 is 2. Correct? So what is f of 1? You just plug 2 here, and what do you get? 3, right? So this is 3. Do you understand what I just did? This is just, okay, so f square m is just f of m, right? That's it. So the output is input for the next step. Okay, so what is f applied to this? 4, okay. What is f applied to this? 4. You get 6, right? We've already had this here, okay. So then I can fill this in 2, 3, 4, 6. But what happens if I plug in 6 here? 6 plus 2 or 3. 6 plus 2, 8. I get 8 here, right? Then 3, 4, 6, 8. Now 8 plus 2. So I get 10. And something will happen later. Let's not worry about it. 4. So I get 6, 8, 10. And then what do I get? 10 plus 3, right? So I get 13. Okay. So what about 5? 5 didn't appear anywhere here, right? Till now there was no mention of 5. So 5 should be interesting. 5. What is f of 5? 7. What is f of 7? 7 plus 2, 9. Excellent. What is f of 9? 9 plus 3, 12. What is f of 12? 12 plus 3, 15. Excellent. Okay. So 6 we've already seen, right? 7, so I'm not going to write it down because 6 this will come here, then 8, 10, 13. And what comes after 13? 13 plus 3 is 16, okay? So same thing, 7, 9, 12, 15. What will come after 15? 18, correct. 8 is also done, 9 is also done, 10 is also done. So let me start here. So you can fill those in. So since I don't have enough space here, so I'll just say ... So 11 did not appear, right? So let's try 11. What is f of 11? 14. Excellent. Sorry, what? 14. Yeah, I heard something else. Okay. What is f of 14? 17. What is f of 17? 21. Excellent. What is f of 21? 25. Okay. So 12 was already there. 13. Okay, let me try. Okay, so I actually have a really long list. But I cannot write it down. I have like up to 106 iterations there, but it's a really long list. Okay, so let me see here. So I'm going to just mark some of the numbers here, which I feel are interesting. Okay. So honestly, I'd encourage you guys to write more numbers and make this table slightly bigger, because we don't have enough information to make nice observations. But I'll sort of lead you guys towards some of the things that I want you to think about. Okay, so let me just make a statement here that when I look at each row, in each row I find at least one perfect square. Okay? This is my statement. My statement is, or whatever, my statement is, when I look at each row, what is each row? I start with an m, then I look at f of m, then I look at f of m, f of f of m, and so on, right? I get an output, which is my new input, and I keep iterating. And my claim is that in each row, I get at least one perfect square. Well, this is at least whatever I've written here till 4, I get that, right? So if you don't believe me, let me try writing down a few more of these, and let's see. So I wrote 50, right? So let's start with 50, which is not a perfect square. Then what comes in after 50? 57. What should come after 57? I already got a perfect square here. Okay, I got a perfect square. Okay, let's try 51. I get 58, right? What do I get after 58? What do I get here? Yes, 65. What should I get after 65? 65 plus 73, right? What should I get after 73? Is that a perfect square? Yeah, see? I got a perfect square right here. Okay? If you still don't believe me, I mean, whatever numbers I write, you can always say that I've carefully chosen those where I get a perfect square. Okay? You're allowed to say that. So let me start with 101. 101 goes to, sorry, 111. Is this a perfect square? No. Is that a perfect square? Yes, see? We got a perfect square. Do you want to try one more? Yes. Yes. Sorry? Oh, no, I can write down there. Sure. So? Hmm? Hmm?
You get 25, the next square. It first begins.
Okay, so how do you want to explain this? Oh, you don't know. Okay, you just made an observation. Okay, fair enough. So my claim is that in every row, I should get at least one perfect square. Okay? And I did demonstrate, oh, I was going to do 103, right? Just to, you know. What comes after 103? What should? 1, 1, 3. Okay. Then 123. Then plus 11. 134. Oh, 1 f of 1. I mean f2, f3. Okay. What comes after this? 145. Okay. So we are already at f4, right? And we haven't gotten a perfect square. What comes after this?
157 and then 116.
Ah. What comes after this?
116.
157. 157 and
116.
169.
13.
Whew, finally, right? So this is m, f of m, f of f of m, f of f square m, 4, 5, 6. So for 103, we had to go 6 iterations to get a perfect square. But we did manage to get a perfect square, right? Maybe for a moment you thought here we won't get a perfect square, but we did hit a perfect square. Okay? So, do you believe me when I say that for every m there is an iteration such that f of that is a perfect square? Why would you believe that? Why should something like this be true? Why should something like this be true? You see any patterns here that might explain this statement that I just made? Okay, I should look at what time it is. Okay. You see any pattern here that should explain the statement? See, if I have a perfect square, then I'm done. Correct? The 0th iteration gives me perfect square. Right? Agreed? So I don't really have to worry about perfect squares. So I have to worry about numbers that are not perfect squares. Agreed? Fine? Okay. So let's look at the next consecutive number. So I have a perfect square. Let's look at the consecutive number. So 1 is a perfect square. Let's look at 2. At which iteration I get a perfect square? Second iteration. Now the next perfect square is 4. Let's look at 5. Which iteration I get a perfect square? Second. So after that, perfect square is 9. So I should be looking at 10, which I haven't, but I could, right? I have 10 here. After 10, I get 13. After 13, I get 16. Aha. So 10 also at the second iteration gives me a perfect square. Then comes 16, correct? So after 16, I get 17, correct? So let's look at 17. Second iteration, I get 25. Haha, I do, right? Then comes, sorry? No, the next perfect square after 16 is 25. I haven't written, but 50 is after 49, which is a perfect square, right? So 50, 57, second iteration is 64. Haha, yes. It goes kind of far for 12? Okay, let's not worry about far. Let's worry about close, okay? Because that could be easier. I don't know, right? 101 is the number after a perfect square. Second iteration, you got 121. Is this what is happening? Is this what is happening? At least for a number which comes after, immediately after a perfect square. Can you explain this behavior to me? Because see, if you look at which iteration you get a perfect square, there doesn't seem to be a nice enough pattern, right? Sort of it goes far, comes back, 12 according to him is really far. So at least for numbers immediately after a perfect square, something nice is probably happening. We don't know. What's your guess? What's your guess? For numbers of the form m square plus 1, right? Or whatever, k square plus 1. Okay? So, why don't we actually do some calculations and see what is happening? So, let me, okay, so since we don't have enough room, I'm going to erase this, but I hope you have written down this table or possibly more entries. I want you guys to make more observations. One observation I did make for you, which was this numbers which are immediately after perfect squares. But what about other numbers, right? Okay, so if I have a number which is of the form k square plus 1, what is f of k square plus 1? I get k square plus 1 plus k. Right? Now what is f of this? So f square of k square plus 1 is this whole thing plus the square root of integer part of square root of this, right? K square plus k plus 1 plus integer part of square root of k square plus k plus 1. Now what is the closest perfect square to this? K square, right? It's not k plus 1 bracket square, it's k square. But what is k plus 1 bracket square? It's k square plus 2k plus 1. This is smaller than that, correct? So the perfect square which is smaller than k square plus k plus 1 is k square, correct? So this is k square plus k plus 1 plus k, which is k square plus 2k plus 1, which is k plus 1 bracket square. So we have a proof of this. And does it coincide with our observations? Correct? So let's look at f of 5, right? F of 5 was 2 square plus 1. So what is f square of 5? What was that? Can anybody tell me? What is f of 5? 9, right? This is f of 2 square plus 1, which is 9, which is 2 plus 1 bracket square, right? And we actually have a proof of this, right? So if we start with a perfect square, we already have a perfect square. If we take a number immediately after a perfect square, in 2 iterations we get a perfect square. In exactly 2 iterations we get a perfect square. And we also know what that square is. That is k plus 1 bracket square. Would something like this work in general? What do you think? What's your guess? Okay. So I want to move to a different problem. So I'm trying to wrap this up. Would something like this work for k square plus 2? Would k square plus 2 be a perfect square for some k? Yes or no? Okay. It won't be. Consecutive squares, do they differ by an even quantity or an odd quantity? Odd, right? Because 2k plus 1. Consecutive squares differ. So k square plus 2 will never be a perfect square. Okay. So what will happen for k square plus 2? So you would have k square plus k plus 2 here. Correct? So that is definitely not a perfect square. But will it be k plus 1 square? What does our table say for numbers, two numbers after a perfect square? When do you see a perfect square? If you refer to the table which was here and I just erased it. Sorry? Okay, so you're saying that a statement like this should be true, that f4 of k square plus 2 is a perfect square? Is that what you're trying to say? Okay. Do you see it in your observations? Do you? Okay. Huh. Okay. 25. But 18? Okay. So at least there is some observations that we have to support a statement like this. Right? What about k square plus 3? Can I make a statement saying that f6 of k square plus 3 is a perfect square? In general, can I make a statement like this? f2j of k square plus j is a perfect square. Would a statement like this be true? I'm just guessing. But that's not a random, that's not an arbitrary guess, right? I'm looking at the table. Okay, okay. But is this true? Is this true? Did you observe it for j equal to 3? Did you observe it for j equal to 3? Okay, what is the time? Hey, so do you remember the row of 3? What comes after 3? 4. So then this is wrong, right? What I've written here is wrong. because 3 is perfect square plus 2. 1 plus 2. 1 is a perfect square. But then f of 3 is 4. I don't have to go, in fact, what is f4 of 3? Which is not a perfect square. Okay, that's what I call guessing. We don't know, but yeah, that's exactly what I'm leading to. It's fine. So, it's like landing on our feet. We made the thing, and then we realized, it doesn't even work for k equal to 1. So, okay, it doesn't work for k equal to 1, but it should work for other values of k. But now we have to be a little bit cautious, right? Because now the base case itself was dicey. So, we don't know whether it'll hold true for other values of k. But this is not statistics where it works for most of the people, so it should work for everybody. That's not what it is, right? It's not majority here. If it works, if I want to write this as a rule, it should be satisfied for all values of k. Or you have to, give some rule that says k has to be at least this, and it works. But do we have a proof of that this actually works? Okay. Okay. Is this problem becoming sort of boring? And yeah, what is this? Okay. I don't want to spend time answering this question that there's always a perfect square. So let me tell you the answer. Yes, there's always a perfect square. But at which iteration, I'll leave it up to you to figure out. I'll leave it up to you to figure out why something like this is true. So the first step is to actually come up with a proof which says that there will be at least one square. And the next step is, depending on the value of m, if you can write down at which iteration you get the first square. Okay? If you start with a perfect square, then you start with a perfect square. If you start with the consecutive, the number immediately after a perfect square, second iteration gives you a perfect square. In general, which iteration gives you a perfect square? Okay? These are some nice questions you can think about. And we've already made a table. You can make even a larger table. You could just use Excel sheet to make a table. You don't have to write it down. But writing down might be more insightful. And I invite you to make some more observations. For example, you can ask next, do I always get cubes? Or do I ever get cubes? If I get cubes in a row, is there something special about m? Or I don't get, or there is nothing special about anything, and this is just completely random, or there's unexplained phenomena there. Okay, I invite you guys to look at that table and come up with more observations. Okay. Okay, so let's change gears, and in the remaining 25 minutes. Yes, you have a question. Okay. Okay. Question for which I don't have an answer right now. Because this is something I thought for training purposes, not for proof. You want real life application of this? There's no prediction here. We want to find a formula that works. But we can always find a huge number, no? You always add 1 to the huge number that you know, and you get the next huge number. Okay, we could talk about this later, but I didn't have any real life application of this in mind, other than demonstrating this guessing and hunching and experimenting. Okay, sort of an open-ended thing. Okay, so let me move to a problem in geometry. And okay, so my problem is follows. So I assume that you at least intuitively know some notions from solid geometry. For example, I hope you guys know what a plane is. Let's not worry about its precise definition and whatever, right? So you sort of know what plane is. For example, where I'm standing, the stop is part of a plane. Plane extends in all directions, like analog of line in Euclidean plane. So it's a plane in the 3 space. Okay. Suppose I were to draw 5 planes in 3 space, in how many parts these planes would cut the 3 space or divide. Okay, if I were to draw 5 planes in 3 space, in how many parts the space gets cut up? Answers? Guesses? 6, okay. Would you like to explain why? Okay. Okay, okay. So are you assuming that these planes are stacked parallel? See, suppose I draw the cross section of the plane. Suppose I draw cross section of the plane, right? So this is my cross section of the plane. So this is my first plane, second, third, fourth, fifth, correct? 1, 2, 3, 4, 5, 6. Yes, 6 parts. Correct. But then the planes, yeah, okay. Okay. No, this is not stacking. These planes extend all the way up to infinity in all directions. Okay, so you can't really place them next to each other. Doesn't make sense. It's like lines, you know. That's what I'm saying. Think analogously. So I've drawn lines, 5 lines in plane. Plane gets divided into 6 parts. Yeah. See, but 5 planes parallel is a very special condition, right? You have to do some extra efforts to arrange them parallelly. If you were to just do it generally, where you don't have any specific relation concerning these planes, what's the number of pieces they would divide the space into? Yeah. Yeah, sure, why not? If they intersect, they'll actually create more pieces, no? Okay. Or you think 8? Okay. Anybody wants to add to this guess list? No? Okay. So at the most, if I see, 6 is at least, right? Do you agree that 6 is at least? See, when I said that I want 5 planes so that there is no specific relation concerning them. It sort of means that my 5 planes are in, general position. Okay, so they don't have any special property. For example, all of them being parallel, all of them passing through a single point. Okay, that's a very special condition. So if I say I want my 5 planes are in general position, okay, or there's some work to do, but equivalently I can say that the maximum number of parts that I would get. Yes. Yes, in some sense. Yes. So the idea here is, if you want to get maximum number of pieces, you would have to avoid redundant intersections. Okay? Suppose 2 planes intersect, so they intersect in a line. Now when you cut by a third plane, you don't want a cut that passes through the earlier intersection, because that will not provide any more pieces, right? Similarly, you don't want parallel, because parallel would only cut a portion or a half of the earlier. But if you intersect, then you would introduce more cuts. Okay, so you want to avoid parallelism, and you want to avoid redundant cuts. Okay. Oh, you think 16? Why? 2 raised to 5 is not 16. So what's your logic behind 16? Sorry? Okay. 2. So, okay. So let's make a table here. Number of planes and pieces, right? Number of pieces. So I think you thought, why do I, look at 5? Let me start with 1. Okay? Okay, excellent. So you wanted to start with 1. So 1 gives you how many pieces? 2. 2 planes give you how many pieces maximum? 4. Okay. 3 planes? 7. Why 7? Okay. Okay. And is that the maximum? Is that the best you can do? Yeah, I understand. Your cross section looks like this. Is that what you're saying? That's what you're saying, right? Correct. So this gives us 7. So is 7 the maximum possible? Have you seen the 3D coordinate system in school? X-axis, Y-axis, Z-axis, right? So I've got 3 planes: XY plane, XZ plane, YZ plane. In how many parts does these 3 planes divide the 3 space? 8, right? So even this can be improved. You can arrange 3 planes so that they cut the space into 8 pieces, and 8 is the maximum. You cannot improve on that. What about 4? What about 5? Yeah, correct. So the upper. Yeah. Okay. 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 For 5. So 2 plus 4 plus 8. Is that what you're saying? 2 plus 4 plus 8. But then what comes here? So you think 16 should come here? Is that what you're saying? Okay, so 16 for 5 planes or 4 planes? That's my question. Then what should come here? So this thing adds already up to 14. So I don't know how do you get 16 here and not here. Oh, at least 17 here? Okay. I don't know, but yeah, good guess. So you start at the first plane, right? Then intersect by a second plane, gives 4 pieces, right? Now add third plane such that it will be perpendicular to the line of intersection of the previous 2 planes, right? Then we get 8 pieces. Okay? See, 4 planes in 3 space is already hard to visualize, correct? So the first thing that we did was, 5 is just a slightly large number to, visualize. So let's start with 1. It's a good strategy. So we did 1, 2, 3. But now 4 is already a problematic visualization. 11? Oh, you're actually coming down. Oh, here 11. Okay. Okay. And then 16, is that what you're saying? But then it doesn't add up to your logic of adding, right? Okay. Fine. Fair enough. I'll not write anything here as of now. I want to sort of divert your attention to this thing, right? So we had this number 5 planes. Like, why 5? That's what I think you thought. And then you thought, okay, let me start with at least 1. If I can answer, then it's fine. So you tried 1, 2, 3, but then even 4 is causing a problem, correct? And mainly because we are not used to visualize in 3 space. So let's consider an analogous problem. Let's consider an analogous problem which is easier to visualize. Instead of this problem, let's think about another problem and hope that solving the other problem help us. Okay? So let's say some lines in a plane. Instead of planes in space, let's think of lines in plane. Let's say 4 lines in plane. Okay, let's think about 4 lines in a plane and hope that problem is easier to solve and it helps us get insight into our original problem. So 1 line breaks the plane into 2 parts. 2 lines in 4 parts. Now add a third line, right? So third line should not be parallel to the previous lines, and it should not pass through the common intersection point. That's the only I get. So how many parts do I get? 7, right? Now the 4th line I should draw so that it's not parallel and there is no triple intersection. So the only way I can draw this is something like this. Correct? Sorry. So just assume that this is a straight line. Okay? So how many pieces do I get? 4 more. Correct. 4 more, because this is the 4th line, right? This is L4. It cut here, here, and here. So 4 more. Okay. So let us write this down. Okay. So here I'm just going to write number of cuts and number of pieces of plane and number of pieces of 3 space. Okay? So if I have one cut, if I have one line in a plane, it breaks the plane into 2 pieces. If I have one plane in 3 space, it breaks it into again 2 pieces. So here it's 4, here it's 4, here it's 7, here it's 8, right? Here it is 11. Here we don't know yet. What about 5 lines in a plane? 5 lines in plane. 16. Why? Why? Now we should have an answer to this question. Why 16? 5 more, but why 5 more? Yes, why? I want an explanation. Which would work for any number after 5. Exactly. See, the 5th line when I draw, it should cut all the previous 4 lines. Correct? No. So what will happen is, this 5th line will be intersected at 4 different places. Correct? So it will add 5 more pieces. Correct? See, that's exactly what happened to the 4th line. Correct? So there is a cut here. So I get this new region, new piece. This gave me one more piece. This gave me one more piece. And this gave me one more piece. Correct? So 1, 2, 3, 4. Because of 4 cuts to the 4th line, 4 more pieces were added. So when I add a 5th line which intersects all the previous 4 lines, I'll introduce 5 cuts on the 4 cuts on the 5th line, which will introduce 5 more pieces to the existing pieces. So I had 11 existing pieces, 5 more, get 16. So what will happen if I draw 6 lines? 22. And we have an answer. We have an answer. And what is the answer here? Suppose P2 of n is the number of pieces a plane gets divided in by n lines is equal to P2 of n minus 1, right? The existing pieces when n minus 1 lines were divided, plus P1 of n, which is just n plus 1, right? What it means is that n points on a line. Sorry, n minus 1, right? Oh, no. What am I saying? Sorry, nth. Yes, this is correct. Where this thing is precisely n plus 1, correct? So I get a recurrence relation, which I can solve because I know what P2 of 1 is. P2 of 1 is 2. So I can solve this recurrence relation and I get these numbers. Okay? So we have solved this problem for lines in plane. Now let's come back to planes in 3 space. How do we do that now? Since we're sort of running out of time, so I'll probably not answer this question, but I really want you guys to think more about this. It's not a terribly difficult question. I want you to think about this, how to get this. But okay, so let me stop just solving things and whatever I did, let me put it in perspective. Okay, let me put it in perspective. So the thing is, first of all, we should not be afraid of guessing in mathematics. Okay? It's not that guessing doesn't lead anywhere. It does lead somewhere. Okay? But what we need is we need enough information, enough observations, so that we can make guesses. We can make educated guesses, right? So there's a difference between wild guess and educated guess. So I'm not going to talk about that, but I hope you would, sort of get an idea as to what I try to say here. So first is we should not be afraid of educated guesses. It's okay to guess in mathematics. Okay, and this whole attitude of doing mathematics is called inductive attitude. So is that what it sort of simplistically what it means is that you look at observations, you try to find a pattern. Based on patterns, you make conjectures. Okay, what a conjecture basically means that this should be the pattern, right? That form. So for example, we wrote down that f4 of n square plus 2 is always a perfect square. That's a conjecture. Even before we had a proof, we said, oh, something like this formula should be true. That's a conjecture. And then we try to find evidences that support a particular conjecture. And unfortunately, we had one example where the conjecture failed. Is that 3? 3 is of the form n square plus 2, but our conjecture was already false. But then is it possible to modify the conjecture, hypothesis, or you have to change the conjecture entirely? Okay. Then we move on to again, sort of the similar step. We have modified conjecture. We go on looking for evidences that support this conjecture. Okay. And we get all these things and try to get the right answer to our question. Okay. Here in the second example, what we saw was we had a very particular problem, 5 planes. Right? Then why 5? Let's try to ask a very general question, n planes, and hope that the answer would be easier. See, if you start by saying n planes, then it gives you freedom to choose smaller values of n. I mean, for all n you shouldn't be scared of all n's, because that gives you freedom to work with smaller values of n. That's what we started with, right? Smaller values of n, which were easier to describe. But then there was a stage we found it's difficult, So then let's move on to an analogous problem in a simpler situation, which was very easy to solve. And we are hoping that the solution to an analogous problem in an easier situation gave us insight to work with this difficult problem. Okay. So since we don't have enough time, but this definitely gives us some insight to the solution of this problem. And the insight is precisely that when I'm going to add, so I already have 3 planes, correct? Which give me 8 pieces. So now I have to add a 4th plane such that it is not parallel to any of the previous 3 planes. It doesn't pass, it produces new intersections. So it should be intersected by, yes, each of these 3 planes, previous 3 planes. But 3 planes intersecting on the 4th plane, if you look at the 4th plane, this is nothing but 3 lines intersecting on a plane, correct? If you look at the cross section, it is 3 lines on a plane. So we are now back to this, 3 lines on a plane. So that solution is definitely going to come handy here. See, that's what happened with 3 planes, right? We had 2 planes, we added a 3rd plane, such that it got intersected by both the previous planes. Okay? I'll leave it up to you to find the answer. But with this, I would like to end whatever I wanted to say. If there are any questions, we can talk about now or maybe later. Yeah, so I know that I haven't answered either of the questions, and to begin with, I planned not to answer either of the questions, because my plan was not to give you answers of the question, but to demonstrate a process of doing mathematics, okay? And could be a little bit vague. I know, because I don't know exactly how to teach this, but maybe I should have said it at the beginning, but there was a famous mathematician, George Polya, who was a champion of this plausible reasoning, inductive reasoning in mathematics, and especially in mathematics education. I sort of liked his writings, and so he's written really nice books on plausible reasoning, 2 volumes. You should really read these books. In fact, this particular example is from that book. Okay. But there are also challenges when you want to teach using these kind of ideas, because a lot of stuff sort of seems open-ended, but there are also different insights and benefits of doing mathematics like this, because usually mathematics is discovered by inductive attitude and not by deductive attitude. That's the way we learn in schools. That's not how mathematics evolves, right? Okay, but it's not very different from any other experimental science when it comes to evolution of mathematics. Any questions? No? Okay, thank you.
Let's thank Priyavrat sir for his lecture. It was very interactive. I hope you all enjoyed it. Now we'd like to remind all our viewers that the S.T.E.M.S exam is on 12th and 13th January, and register online on our webpage. You can find the links in the description of the YouTube video. And that's it for this lecture.
Did you like this lecture? Brilliant's logic course has a lot of fun puzzles for you to help learn.